Welcome to the Nanovation Podcast. Information about this and other episodes can be found at fillerlab.com/nanovation. If you like what you hear, be sure to tell a friend or leave a review at Apple Podcasts. It really does help. I welcome your thoughts and suggestions. You can contact me on Twitter at Michael Filler or via email at nanovationpodcast@gmail.com. Hey everyone, it's Mike. Because October is one of the busiest months on college campuses the world over, we're replaying a great episode from the Nanovation archives. But fear not, in a few weeks we'll be back with new shows and some great new guests. Stay tuned. What do you get when you combine current events and nanotechnology? NanoBama, a carbon nanotube-based picture of the 44th President of the United States. Today, John Hart, the leader of the Mechanosynthesis Group at MIT, joins the podcast to talk about his love of nanomanufacturing and science communication. We talk about the challenge of developing code for nanomanufacturing processes and how nanomanufacturing is in a sometimes frustrating adolescent phase. John also shares his experience preparing for and presenting a TEDx talk. This is the Nanovation Podcast, an exploration of big innovations emerging from small things. I'm Mike Filler, your host and a professor at the Georgia Institute of Technology. Enjoy the show. Today I have John Hart here, and it's kind of hard to find your official title. I think, and you can correct me if I'm wrong, it's the Mitsui Career Development Associate Professor in Contemporary Technology and Mechanical Engineering at MIT.
Yes, that's correct. And, it's like a statement on academia. Professorships have sometimes weird and obtuse titles that make us sound very highbrowy, but we just want to do the best work we can.
Right. So you do science, basically.
Yeah, I consider myself an engineer, someone who's passionate about understanding the needs of our world and creating new materials and manufacturing processes to hopefully make our lives better, and also educate the next generation of innovators. And that sounds like a big deal. I think it is. Always trying to be better at it. But I think those of us in academia and fortunate to be at great places such as MIT have a responsibility to do that and do it well and continually be refining our craft.
Agreed, and the only way to get better is to refine it, right? So the name of your group, you call it the Mechanosynthesis Group. I'm just kind of curious where that came from.
Yeah, great question. So when I was starting as a faculty member, after I finished my graduate studies, I was lucky to be asked to join the faculty in mechanical engineering at the University of Michigan. Great school, actually, my undergraduate alma mater, and I was committed to finding a name for my research group that I thought was it, that I loved, and I personally didn't favor the group being named after myself, just because I wanted it to be a different name, right, to represent the mission, and I thought of what I do, which is materials manufacturing, mechanical engineering, and I came up with the word mechanosynthesis, and it stuck. I thought of a whole bunch of other completely odd and useless words, more useless than mechanosynthesis perhaps in some ways, and then it stuck. And actually I looked it up and I found that mechanosynthesis is the word that some of the initial sort of speculators about nanotechnology used to define the potential process of mechanically building materials one atom at a time. And that's not what we're directly doing, or I think we'll be able to do in the near future. But I kind of like that. That there, it's good if the word's completely unique, but it's also good if there's a resemblance to what you're interested in. Ultimately controlling the making of things at the finest scale possible.
Right, at the finest scale possible is the operative word there. And I guess you're referring back to maybe some of Drexler's vision and things like that with regard to assemblers and such at making atomically precise things. But last episode, I talked with Charlie Bennett, who's a friend and colleague here at Georgia Tech, about kind of the early visionaries in nanotechnology and then the controversies that have emerged over the years. And we talked a little bit about why, in some cases, it's very hard to think about scaling down mechanical things all the way to atoms. Now, there's a lot we can do, and maybe we'll talk about it a bit in this podcast, but going all the way down, individual atom by individual atom, is an immense challenge, if possible at all.
Yeah.
So you just described what your lab works on in a very broad sense, but I was hoping you could kind of give us an example of one kind of project you're working on, maybe summarize a recent publication, just to give a more specific flavor for the types of things you guys do.
Sure. Well, I'll start with our work on carbon nanotubes. So for many years, in fact, since I was a graduate student, I've been interested in the opportunity for designing and producing new materials that utilize carbon nanotubes. And I recall perhaps in the first episode with Baracola, you were talking about carbon nanotubes, of course being cylindrical molecules of carbon with exceptional mechanical, thermal, and other properties. And a great promise comes if you're able to assemble or configure carbon nanotubes into things like fibers and wires, or deploy them in composite materials, or organize them on surfaces, or incorporate them as elements of electronics. So one specific area within carbon nanotubes that we've been working on involves the manufacturing of carbon nanotube surfaces, as we call them. And what I mean by that is microstructures of carbon nanotubes. So imagine each one of them as like a little building, meaning it's a roughly polygonal three-dimensional structure that contains a large number of nanotubes aligned in parallel. We call that alignment a forest, because if you zoom in really close with an electron microscope, you see the nanotubes that kind of look like trees in a dense forest. And we've been working on how to synthesize the nanotubes. We call it growth, though it's a chemical reaction, how to pattern them and how to shape them and how to control their properties in this format of a nanotube surface. So many nanotube microstructures on a surface where their properties as a collective are controlled. Their mechanical properties, their wettability, which means how they interact with liquids, their thermal conductivity, their electrical conductivity. And in particular, we figured out how to control the growth process to make the nanotube structures fairly dense, as well as to shape them into unique 3D forms. And that's a bit vague, but what I mean is instead of having the nanotubes grow up straight perpendicular to the surface, having them bend in a particular direction. And that means we can control how liquids interact with the surface, or how much force it takes to compress the surface, and maybe it will stick, or by applying an electric field, you can get the nanotubes to pick up an object. So we think that this opportunity to control the properties of surfaces in contact is a very big one, and there are unique characteristics of the nanotubes and how we make them that lets us turn this into a platform technology for surface engineering.
You have a great picture on your website where you have some of these kind of pillars of nanotubes you're describing, and the one I'm thinking of is it looks like each pillar has been twisted.
Okay, yeah. So that was those twisted pillars were created by another step after we produced the nanotubes using liquids to shape the nanotubes. So we studied for several years how you can use capillary forces, and capillary force just means a force exerted by the surface tension of a liquid, to take the nanotubes that we grow in a simple shape and basically twist them into a more complex shape. And one example shape we demonstrated are these twisted pillars, and we basically understood the instructions, if you will, of how we wanted to pattern and grow the nanotubes, so then when exposed to a liquid, essentially condensation of a liquid onto the nanotubes, when the liquid then evaporated, it would cause the nanotubes to collectively twist up into a spiral. To me, it's a nice example of a scalable process because we're able to control the growth of the nanotubes in parallel over a large area. We can apply a conventional lithography process to pattern the nanotube growth, and then we can apply a simple instruction, capillary forces. We called it capillary forming, where we condensed a solvent, and if we understand the physics of interaction between the liquid and the nanotubes, we could cause a transformation to take place. And we didn't have to go and grab every nanotube with a little manipulator. We could just do it via conditions we apply to the whole area of nanotubes at the same time.
I see. Okay. Did you know ahead of time that you would get that effect, or was that one of those things that was serendipitous in the lab?
It was the shrinkage of nanotubes under capillary forces is something other people had studied, but they had studied it in a different way. It was serendipitous for us to think of actually condensing the liquid onto the nanotubes, and then as we tried to understand the process, we had the idea that if you condense the liquid and you confine the liquid into each pillar of nanotubes, you can then sort of isolate each pillar, and if you isolate each pillar, you can figure out how to shape it so you can get these complex shapes to be formed. So the twist was engineered. We sought out to achieve that particular shape, but the whole process of discovering these instructions for manipulating nanotubes using capillary forces was sort of both serendipitous and guided.
Yeah. Okay. I like your use of the word instructions, kind of like the code which we're using to program the manufacturing of the material.
Yeah, I agree. And when any process, to be consistent, we need to understand the instructions. The challenge with ultimate nanomanufacturing, or how I would define nanomanufacturing as controlling the architecture and properties of matter at the nanoscale, is that we don't know all the instructions, and we don't know how to implement all the instructions that we do know. So we need to rely on new ways to control those processes.
Yeah, and that is summed up really nicely. The central challenge of nanomanufacturing is both the what do you want to do to the material and how do you carry it out. Both of those, and I think people underappreciate the importance of what I'll call a manufacturing system in the advance of technology. When I say manufacturing system, I'm thinking of the assembly line. And there's even earlier examples, and I forget the years, but back in the early days of not the early days, but when people were still building ships hundreds of years ago, there were several breakthroughs where rather than one person specializing in the entire ship construction, it was then for the first time broken out where individual craftsmen did individual pieces and then everything was assembled. And so you parallelized that process. And that was another example of a breakthrough in ship manufacturing that led to, I forget which group of people it was, but they were dominant in the seas for many years after that. And so I look at nanomanufacturing as the same kind of thing. What are the new manufacturing systems that are going to be the platforms going forward for the next several decades?
Yeah, and that's a great question. I don't think we entirely know, and with that we have to appreciate that nanomanufacturing, however we define it, must fit into the context of manufacturing at large. And there are already many products where we use nanomaterials or nanostructured materials, even if they are not as complex in their architecture or controlled at the molecular scale, but arguably are an instance of nanotechnology, from simple to complex, if you will. From the thin film coatings on every one of our electronic devices, where the transparent conductor, typically made of indium tin oxide, is a nanometric film whose optical properties and electrical properties have been optimized for best performance, all the way to advanced drug molecules that are molecularly engineered structures designed to execute specific tasks within our body.
And in between there may be transistors.
Yep, transistors. Yeah, nanotechnology at large. Yeah.
Yeah.
Exactly.
So let's talk about this a little bit. Where do you see opportunities to create these kinds of things at scale? With the kinds of, and maybe we should talk about the metrics that are valuable to think about when you're talking about nanomanufacturing at scale. So clearly there's control of the structure itself, and the structure will then dictate, of course, the performance and the function of the material. What does it do? How does it conduct charge? How does it wet? All those things, right? So you need to control that. And then you need a sufficient throughput so that you can actually make enough to affect people's lives. And you need to do it efficiently from a cost perspective, and thus you need high yields. You don't want to waste a lot of material and things like that. And from those kind of three perspectives, can we talk a little bit about what we're good at, what we're not good at, and maybe it's a combination of all three for different technologies. But I'm just kind of curious what your thoughts are there.
Yeah, as I'm hearing you ask the question, my mind's sort of drifting off on a bit of a tangent, and I'm trying to draw a parallel between the evolution of macro-scale manufacturing and what might be the evolution of nanoscale manufacturing or nanotechnology. And as we've seen, industries rise over the past 100 years, a lot of manufacturing has gone from craft to sort of codified knowledge, and so many of the products that are around us today are complex. Of course, they involve many different materials and manufacturing processes. But I feel one differentiating factor in the past 5, 10, 20 years is that we really now experience and leverage the integration of design and manufacturing. We are able to design objects based on the capabilities of manufacturing processes, and we are able to advance manufacturing processes to enable designs. This is a bit of a tangent, but I teach a big manufacturing course to undergraduates at MIT, all about manufacturing processes, and one of many examples I use is the iPhone. And one specific part of the iPhone, which is the housing. It's made out of aluminum currently, and it's CNC machined. And Apple in 2015 sold over 150 million iPhone 6s, and each one of those had the same CNC machined housing.
So let me stop you real quick.
Yeah.
So just describe what CNC machining is.
So CNC machining, CNC stands for computer numerical controlled machining, and it's basically an automated machine tool which removes material using a rotating bit. So a milling machine, it looks like a drill machine, but it moves a rotating tool around in typically 3 or more directions. And you can take like a block of aluminum and you can remove aluminum to have a particular shape you want, like the housing of your iPhone or the housing of your MacBook.
Right, and the key part is that you start with a big block of aluminum and you cut out what you don't want.
Right, like we would call a top-down process.
Yeah.
And there's an analogy to nano being bottom-up right there. Why I'm going on about the iPhone is that if you look closely at that, you see that it's just one piece of the phone, and it's arguably one of the quote dumbest pieces of phone. It's just the housing, but you see the detail that went into the design for that, all the internal features and fasteners and its shape and how it's coated, and that essentially enables the phone to be lightweight and stiff, and Apple to realize the appealing visual designs that it does. Also, the fact that Apple can command such a large market means that they can invest so much money in understanding the process. And the capabilities of machining and how they've advanced the automated machining and other aspects of that enable the design. So I think in addition to the manufacturing, which I want to get back and talk more about, we'll really start to see a revolution in nanotechnology more broadly when we can design materials to achieve particular properties and manufacture them. So not only I want to make, a large quantity of carbon nanotubes in a powder or on a surface, or I want to assemble nanoparticles into some particular, array that's very well organized, but I can design that assembly to have a particular property and then achieve that property by design. And right now, when Apple designs the housing for its iPhone, it's probably saying, well, how much force is going to be exerted on the phone when the customer drops it or the customer puts it in their back pocket and sits on it while they're on the subway. And then they choose the thickness of the material and they simulate how it's going to deform and is it going to break and so on. And our ability to do that at the nanoscale in an engineering sense is going to be essential to enabling technology.
Yeah, it's a great point, and I think my gut feeling is we're still limited in the fact that when we try and make some of these materials that have various hierarchies, even if you're taking carbon nanotubes. Actually, I should be careful because that's your expertise. But if I take these building blocks, and I'll just use carbon nanotubes as an example, and I try and put them into a certain orientation and relative to each other, and let's call it a mesh or something like that. Having processes that create the same structure every single time still seems like a challenge to me. Maybe for carbon nanotubes, people have figured it out, but for all the plethora of other nanomaterials that exist, the different shapes and the different types of materials they're made from, we're still at early stages of being able to do that.
Yeah, you're right on, and one issue with that is that the forces that you have to apply, for example, to move and position nanoscale structures are very, very small. And if you make an analogy to a robot that's used in macro scale manufacturing, it's not easy to make mechanical robots that are on the micro scale or the nanoscale and can pick and place individual objects. Let alone the fact that if you were picking and placing the individual objects, it would take a long time if you just had one robot or 10 robots. The other issue is that nanostructures are sticky. There are intermolecular forces between structures, and that means that it's not easy to position structures and overcome those forces relative to the dimensions at play. There's also the issue of noise. Just the fundamental aspects of matter mean that structures that are small move and vibrate in a random fashion, especially if you have them in a liquid environment or a gaseous environment. And it's not like if you necessarily put a basketball on the table, if it doesn't roll around, it's going to stick there. Put a cardboard box on the table. If you put a nanoparticle on a substrate, it might move around. So in some cases, it may not be possible to achieve that ultimate level of control unless we're able to overcome, those other forces at play. So to me, back to the applications, it's also understanding what we really need. Like, when we make something at the macro scale, iPhone again, Apple says, here's specifications and tolerances. I want this hole to be 1 millimeter plus or minus 0.01 millimeters. What are the tolerances we need on the position of the nanotubes, on the diameter of the nanoparticles to be able to achieve the desired function? And not only is the manufacturing process critical, also critical to manufacturability is the measurement techniques. And in terms of processing technology, I feel that advances in measurement and metrology are as critical as advances in the manufacturing technology itself.
Yeah, and I completely agree with the need for faster, more inexpensive metrology at the nanoscale. I mean, we're for the most part, well, in the research world, we're still stuck with TEM and SEM, and they've gotten better and faster and all of the above, but there's still a huge cost barrier there, and it takes a lot of time. And so we need something that's as simple as, let's say, well, measuring with a caliper or using spectroscopy, which is very commonplace these days for molecules, let's say. And we just don't have those things yet.
Yeah, we don't, and like you say, we can use the high-end tools that are time-intensive and labor-intensive to enable our discoveries. But to translate to production, the measurement techniques need to be cost-effective, need to be rapid, and also need to be quantitative. If you take a caliper or now even, take out your smartphone and take a picture of something, you could pass that through an image processing algorithm. It could say, like, what's the diameter of the apple that you're photographing? But when it comes to, looking at a forest of carbon nanotubes, even if you can take a beautiful picture with an electron microscope, say you have a specification that the diameter of the nanotubes has to be 10 plus or minus 1 nanometer, you need to be able to extract that information. So maybe in the next 10 to 20 years, these characterization instruments will become more compact, more cost-effective, and also will have better, essentially signal processing techniques to be able to get the numbers in addition to the pictures.
Yeah. And then thinking about things that may even be useful for inline metrology. So there's kind of, right, there's two levels of this. It's let's get better so that when we develop new things, it's easier and more streamlined. Then there's also, I need to be able to monitor a process in real time in a manufacturing environment. How do I do that when some sheet where I'm putting nanomaterials down is moving past me at 1 meter a second?
Yeah, exactly. And I may not need to know the exact diameter of the nanotubes, but I need to be able to measure something that indicates that the diameter is correct.
Right.
So maybe I measure how it responds to microwaves or something, and that is an indication of the thing that I'm looking for.
Agreed. So then we have these various pieces that are all still in flux in the nanomaterials, nanomanufacturing world, and I'm curious. I feel like carbon nanotubes, and maybe you could even argue things like graphene, are definitely the furthest along. And we have companies like NanoMech and NanoComp, and they've come up on the podcast in the past and working on deploying carbon nanotubes in lubricants and in fabrics and all that. And I'm kind of curious, with what you see going on today, that stuff, I'll call that exists. What's the next kind of big wave of materials or applications that are going to be nano-enabled? Do you have a sense for that?
That's a very good question. It's hard for me to say other than to broadly say I believe we will enable true engineering of nanomaterials for specific applications. I think in addition to carbon nanotubes, where you've discussed nanotube fibers and nanotube thermal interfaces. There are already products on the market or coming onto the market, even if the markets are small. There's also many examples of nanostructured coatings. There's an MIT spin-out, I believe, called Xtalic, which produces a hard-wear-resistant nanocrystalline metal coating, and that's used on connectors, billions of connectors around the world, like the thing you'd plug in to charge your smartphone. There's also interesting nano-enabled work in quantum dot televisions. And another local company called QD Vision, I believe, was the first to partner with an electronics manufacturer, Sony, to bring out a television that uses quantum dots. And this is a really interesting story I heard the founder tell in a seminar here about the history of their company, QD Vision, and what they went through in trying to develop different products using quantum dots, essentially semiconductor nanoparticles as lighting and so on. But what it ended up as is they partnered with Sony to create basically a plastic tube filled with quantum dots sort of frozen in plastic that converted light from blue LEDs to a very pure white color spectrum. And that is the light that's used to backlight an LCD TV. And their claim was that technology enabled the TV's color spectrum to be, more natural than any other TV on the market before. Actually, when we moved to Boston a few years ago, we needed a new TV, so I bought one of these TVs, and it's a really, really nice TV, and I feel proud that it has nano in it. Yeah. But the nano in it is in some ways simple, and in some ways very exquisite. We think sometimes of nanotechnology as the ultimate limit, right? The atom assemblers and the perfect lattices of nanotubes or nanoparticles. This is quantum dots, semiconductor nanoparticles, sort of randomly frozen in a tube of polymer. And it's just one small piece of this television, which has immense complexity in materials and processes. But to achieve that, this company needed to spend many years developing the synthesis technology for those quantum dot nanoparticles and control their size and their composition and their surface chemistry so this could be possible. Not to speak for them, but I believe from hearing the presentation of their story, this was an unexpected product. It wasn't what they initially set out for, but they were able to leverage their expertise in manufacturing these sort of nanoscale building blocks to make the product possible.
Yeah, I think this has come up on a previous podcast. It's a great example of a couple things. One, nano in something real that you can buy. And two, how very often in commercial technologies, it's not what was originally the plan, and that they just realize this is going to be a pretty neat thing to do. I also think, my group works in electronics where you have to make electrical contact to nanomaterials, and that can be a real challenge because they're so small, and just electrical contacts are tough even in bulk regular materials. And so the fact that the quantum dot sits there between the screen and the LED backlight, and it absorbs a photon and just re-emits a photon, it's kind of sitting there by itself doing that process. You don't have to contact it electrically. It just works by absorption and emission is really simple, but I guess exquisite was the word you used, and I think that's right.
Yeah.
Go ahead.
So perhaps this has come up before, but even more so, I think that we as scientists and engineers must still try to focus on the most fundamental enabling problems, but also be driven by applications to try to envision the technology that would be possible from the innovations that we could enable and take that back to the lab. And I like to think of research, at least in the stuff that drives me, as being a combination of basic research to enable new technology. And in the area of manufacturability, we do a lot of work on trying to invent manufacturing processes to realize these new materials at scale. And I think there's basic research that's done in processes that are intrinsically scalable that can help accelerate the realization of nanomaterials with this engineerability behind them.
Can you expand on what you mean by intrinsically scalable versus something that may not be?
So, the question of the scale itself is an interesting word. What does it mean? I believe it means, in the present context we're discussing, being able to produce a quantity of material with appropriate levels of quality control at a reasonable cost. And the cost for some applications may need to be very low, like measured in dollars per gram or dollars per kilogram. In some cases, the cost is maybe measured in dollars per square centimeter or less than that. For a process to be intrinsically scalable, I believe we have to envision the possibility that given probably a lot more engineering stuff beyond the lab, we could implement this process in a manufacturing environment that will allow it to realize those metrics. And in our lab, it's impossible for us to take things to the finish line, but I try to focus on problems and processes where we can envision that finish line being crossed later. And also recognizing that pretty much everything, like I said before, around us is manufactured using multiple processes. The thing that we want to augment using a new material or a nanomaterial is probably not a complete product, but just it's an element of a product. So often what I believe influences strongly the viability of a new process for a new material is its compatibility with all the other processes that need to work in concert to realize an eventual product and the constraints thereof. One classical example, taking carbon nanotubes and perhaps incorporating them in next generation transistors requires processes for not only producing the nanotubes with the right level of conductivity and structure control, diameter, and so on, but also doing that in the context of the other semiconductor technology that deposits and patterns all the other materials, temperature restrictions, contamination restrictions. And that's one of the reasons why we haven't seen nanotubes appear in electronics to date, is because the need to integrate those two processes. And it's not that we haven't seen them because people haven't thought of this, it's just because it hasn't been possible to mutually achieve both objectives.
That's a good point. And related to that, you mentioned transistors, and I look at transistors as the kind of archetypal, sufficiently complex nano device. So, some people look at a transistor, which is consisting of, in the silicon, the source and the channel and the drain that current is transferred across, and then there's this gate that sits on top and controls the transport of the charge below it. And, given some of the beautiful structures people can make today is at the nanoscale, you might say, well, transistors are pretty simple. From another perspective, though, they're remarkably complex because you have a bunch of different materials together, different regions with different conductivity, and you're applying electric fields to control the flow of charge. And one of the things I think is interesting to kind of think about going forward is how do we take where we've been successful thus far in nanomanufacturing of individual nano objects, let's call, say, a carbon nanotube or a silicon nanowire, and create additional nanoscale complexity. So I feel like we're getting pretty good at the individual object fabrication. We're not quite there maybe with scaling the fabrication for all objects, but we're getting better. But I feel like one of the main frontiers going forward is how then within an individual nanostructure do I create additional heterogeneity that gives me a higher level functionality. Does that make sense? Yeah,
I agree. I imagine you're thinking of sort of, making a nanowire or nanotube have different segments that might function as a transistor in combination, and basically designing new building blocks that can have new properties. And I think that is kind of the next generation that we're in now, and it builds on the initial generation of synthesizing these materials, sort of the basic building blocks, and now you can make more complex building blocks. And perhaps that's a better path to bringing these materials in applications such as electronics. If we can say now, instead of just making the existing transistor smaller or faster or a bit less expensive, we can now create an entirely new kind of transistor or computation device that has performance that we haven't imagined before.
Yeah, right. And potentially do it in a way that is orthogonal to the way it's been done in the past. And that I always find so hard to think about because we're all products of the world around us, and to try and step outside of what has been done, who the incumbents are, and for the transistor case, CMOS technology clean room paradigm and photolithography, deposition, etc., and think about doing similar things in completely different ways is, I find, very challenging, but fun at the same time, even if I'm not good at it. If we then extrapolate a little further, now we're kind of getting a little bit away from current, present-day reality, but that's fine. One of the things I think is really limiting, both from the research perspective and probably also the industrial perspective, is the existence or lack thereof of a supply chain. And as a chemical engineer, right, we take it for granted that there is this chemical supply chain that starts with really basic building blocks, oftentimes looks like oil, and other feedstocks. And then there's this whole kind of branching of molecules that have been assembled from those starting products, and then other molecules assembled from those, and people can kind of insert themselves at any point in that supply chain, in that hierarchy of structure and function, and start their process or grab molecules that have been developed at that point. They don't always have to start from the initial feedstock, if that makes sense. Mm-hmm. And I feel like in nanomaterials we're completely hamstrung by the lack of this supply chain.
Yeah, that's true. And supply chains, I think, are driven by markets also, right? Petroleums are derivatized into polymers, and here comes my mechanical engineering explanation of it. But then you can buy polymers, and you can look up their rheological properties, and you can use them in injection molding. You can go on and so forth, and that exists because invention of polymer processing methods, as well as the large markets commanded for it. Right. Nanomaterials, the sort of the classic chicken and egg problem. A lot of investment is required to establish a supply chain for a particular material where the materials are consistent and qualified. And in addition to the fact that we've discussed the challenges of measuring and controlling the output of the process, just the fact that in order to get it right, you need to be able to spend a lot of time and money on figuring out how to make it. The chicken and egg problem, I think that sums up probably everything about nanomanufacturing. It goes back to the earlier discussion of, well, I want this set of properties, but I can't actually measure things well at the nanoscale, and I need to develop those techniques, and I need to then scale the production of the starting blocks, and the building blocks, and then I need to try and construct a supply chain. And I find it challenging to try and come up with ways to think about how this would look, and frustrating at the same time that it's not so easy to go in and pull a nanomaterial that someone else has made and then use it. In fact, I think, and one of the things I try and pitch when I write proposals around this type of thing is, look, for those of you who don't think the nanomanufacturing piece of nanotechnology is important and just think it's just scale up, it's that's just engineering, and it's not gonna, we shouldn't spend a ton of time on it. It ends up feeding back to the science, because when you can do these things well at scale, other people can take that starting material, and now you've pushed the ball down the field far enough that someone who's not an expert in the carbon nanotube synthesis can take the carbon nanotube and study it in a cell or use it in some other kind of material, right? And so you don't always have to go back all the way to the beginning, and that really helps push everything along. Yeah, exactly. And there's a new analogy to looking up in a catalog of mechanical parts, looking up in a catalog of nanoparts, or being able to buy a dispersion of carbon nanotubes that has well-defined specifications that, even if you don't know how you're going to process it going forward into your device, you at least know that you're getting what it says you're getting, and if you order it 10 times, you're going to get reasonably the same thing. But I think we have made progress in that area. With just a personal example, my group is doing work on printing nanomaterials. We've developed some specialized stamps that can print essentially nanomaterial inks with high resolution. And critical to that work was our ability to go to a chemical supplier and identify a series of of essentially nanoparticle inks that we could purchase and then start working with. And I think one of the most difficult things, kind of around the circle here in this nature of research is compounded by the challenges in measurement and characterization, but is codifying knowledge on how to work with materials. When I was in graduate school and I was doing microfabrication in the clean room, where you start with silicon wafers and you have to learn how to deposit this material and etch that material. Everything is a learning process, but all the tips and tricks that people don't intend to hide, but just the native craft, just like the craft of making stuff, is incredibly difficult to codify. And I think as a society, as an academic culture, we do a really poor job in our collective responsibilities in documenting that and sharing that knowledge, and that leads to big interface losses and inefficiencies, and I think it inhibits the translation, building things to the next stage. And until we're able to, do the simulation, design, and make, we're in this era of craft, and that limits our ability to establish the supply chain, like you say.
So, a couple things. A really great point. So I love the hardware store kind of analogy. As a chemical engineer, I think chemicals, but to the average person, right, with nanomaterials, we want to be able to walk into the Home Depot for nanomaterials, go to that section with all of the bolts and nuts and washers, and pick out exactly what we need. And we have nothing close to that right now.
Right.
So I really love that analogy. And then your comment about not codifying the knowledge I find interesting. I'm really curious because I feel like a lot of people would look at academics and say, well, aren't you publishing papers? Aren't you getting this stuff out there? And so I'm curious where you think this is falling through the cracks, or how.
Well, I don't know if I completely know myself, but first of all, I very much believe in the process of academic publication, and writing journal papers to disseminate work is what we should do. If we don't publish that way, what's the point in some regards? But the conventional mode of publishing a journal paper, in some cases, misses some details that might be essential to actually, replicating work. Issue of replication is a whole other topic. Also, perhaps the format in which we write up conventional journal papers is, given the tools we have at our disposal today, not the best way to teach others to learn from our advances. Right? An unavoidable part of the academic circle is to tout the advantages and novelties of the device you make, the properties you achieve, its potential applications. But in many ways, right, the goal of that work is to enable others to take it and build upon it. And the ability of someone else to take it and build upon it is more strongly tied to their ability to repeat what you did, or to, via something like a supply chain, receive a material that's representative of what you used or what you achieved. And that takes a lot of time and takes a little bit of a different focus. So I believe all these efforts to document our protocols, using videos, just using alternative formats of papers is very important. Also, frankly, in maybe a robotic way, kind of codify knowledge, extract statistics, data, process conditions from literature, and kind of learn that way for some things.
Okay, I see what you're saying. And I think there's probably 7 topics in there for future podcasts. So I want to make sure we have time to talk about 2 things. One is 3D printing, both the 3D printing itself and the course you teach, and then also I want to get to your TEDx talk. So let's talk about 3D printing. Quickly give a summary for those who aren't familiar with it, although I feel like it's becoming pretty mainstream these days, and kind of talk about what the challenges are and where you see it going.
Yeah. Thanks for asking. I'm really excited about 3D printing. It's a buzzword to many people in the public at large because I think it's really an important part of the future of manufacturing. I also think there are parallels, philosophically in terms of 3D printing to nanomanufacturing because it's new manufacturing technology with a lot of potential and a lot of challenges. 3D printing or additive manufacturing, as we like to call it now, is the process of building up an object layer by layer. That's the, quote, textbook definition if you go to the standards body that's written this definition for the field. And it's exciting because it offers potential advantages over conventional manufacturing techniques because you can build things that have complex shapes. Different manufacturing processes like CNC machining we described before are restricted in the shapes they can make. But 3D printing, you can make, I'm sitting in front of me on my desk, I have a 3D printed model of the main building of MIT, which was printed in one piece and has all the rooms and columns and cavities inside of it. So 3D printing can achieve those complex geometries. You can also potentially process materials like high-strength, lightweight metals or high-temperature ceramics that are difficult to process by other means. And also, because it's this essentially bottom-up process, we can think about producing products or parts in small quantities. And if we realize our vision for making 3D printing more cost-effective and reproducible, we might see making products in quantities of 1,000 or 10,000, for example, rather than having to command a larger market to invest in the specialized machinery or the specialized tooling that we have to do for an alternative conventional process.
Do you ever see, right, because if we extrapolate out, you said just now, I guess, that you could see this being cost-effective for smaller scale manufacturing. And then I think about something like coffee. And I'm enjoying my coffee right now. Otherwise, I would not get through the day. But
yeah, me too.
So I'll take the U.S. as an example. Everyone has a coffee maker in their house.
Yep.
We're making hundreds of millions of cups of coffee a day in a distributed fashion. And as a chemical engineer, I say that if I want to do it with something more technological, I would say that's crazy. But is there going to come a time where centralized manufacturing becomes less important and these kinds of 3D, this type of manufacture becomes the equivalent to coffee making in our home?
I wouldn't go that far, but
okay.
I think if we think about that limiting case, we can think about sort of an in-between. And on the first day of my manufacturing class, all manufacturing processes, I say, what's your definition of manufacturing? I ask the students, and I say, okay, here's mine. I say manufacturing is value at scale. You provide something that creates value in someone's life, and you produce it at scale, where scale, as we've discussed before, for nano is like high volume, high quality. The idea of 3D printing, producing things on demand in small quantities, is one of, I think, a set of technologies that let us think about redefining those axes.
Yeah.
What is value? Does something have to have value to 1 million people, or in the case of the iPhone, 100 million people? Or can it just be valuable to one person, or 10 people, or 1,000 people? What is scale? Is scale the entire U.S.? Is it just the state of Massachusetts, or the city of Cambridge, Massachusetts, or Atlanta, Georgia? Or is it a different culture or country compared to us? And I think we're seeing that all across manufacturing, from nanomaterials to assemble molecules and create customized therapies, to macro-scale 3D printing, where aerospace companies are using large metal printers to print pieces of airplanes that they couldn't make before, redefining value and scale. And value can be not only value in the end product, but can also be value in the product development process, prototyping something quickly, for example, or accelerating the time to market. There's a great video you could probably find on YouTube about 3D printing, believe it or not, potato chips. Not the potato chips you would eat, but plastic potato chip prototypes that I think Frito-Lay printed to give to customers to say, do you like the feel of this in your hand?
Wow.
And they got feedback, and they said something, I forget the statistic, but like they took their normal process of prototyping other ways and collapsed it by like a factor of 10. And then they were more confident in the investment they had to make in producing the potato chips at scale. They didn't change anything about how they cut the potatoes and so on, but they were better able to engage their customers in the design process.
I think that's great, and then maybe as a I'll come back to that. I guess I have as a segue then into your course. One of the things you ask the students to do, I guess, towards the end is kind of do 3D printing on steroids and say, okay, here is what exists in terms of 3D printers. Now do something beyond that. And you've had people who've made 3D printed ice cream.
Yeah.
Can you describe how they did that?
It's just like creativity, in the guise of an intense class. Just sort of do the craziest thing you can. But they 3D printed ice cream. Number one, their motivation I thought was awesome. They wanted to create this 3D ice cream printer to get young people who, we all love ice cream, but young people maybe really love ice cream, engaged in science and technology. And then second, they did it by hacking together their understanding of ice cream as a material, 3D printing machines, liquid nitrogen, all those things. So what they did exactly is they took a soft serve ice cream like churner bought from Amazon. They put it on top of a freezer, a small under-counter freezer. They cut a hole in the freezer, and they pumped the ice cream into the freezer, in which they took a hobbyist 3D printer, flipped it over, took out the print head and replaced it with the ice cream tube, and inserted liquid nitrogen coaxially with the flow of ice cream, so the ice cream would freeze upon contact. And then they programmed the whole thing to print ice cream. And it was hard and creative and crazy. And by the end of the semester, they were able to print simple shapes, like they made a three-dimensional star of ice cream. But at our expo in the big lobby at MIT, we had all the projects set up, and they were printing ice cream. And I actually took a bite for the first time ever of anything that's come out of my teaching or research.
That's all I was going to say. Also, I hope they were wearing their safety glasses.
Yeah. Liquid nitrogen. Yeah, they had to clear that all with the environmental health and safety, and went through all that.
That's great. I'm curious, before we move on to the TEDx thing and wrap up, is lots of hype around 3D printing for good reason, as you've described. One of the things I'm curious about is kind of additive printing at the nanoscale, right? So we started this conversation talking about nanomanufacturing. And so most 3D printing, at least that I'm aware of, is you're making larger size parts. Maybe it's micro, we can get down to. Where are we in that regard? I mean, if I wanted to ultimately print at the nanoscale in a similar fashion.
So there are many, actually, like rapid prototyping processes for nanostructures that use the idea of locally depositing or positioning material. In the end, we need to do that, but we need to do that at the right scale to make something useful. I don't know if this is answering your question, but in the long run, I see eventually a combination of the bottom-up processes, the self-assembly, where we rely on the interactions between nanostructures to configure themselves, and the top-down, where we place material locally. For 3D printing at the nanoscale, there's a few different machines you can buy, processes people use. One of them is what's called two-photon polymerization, very sciencey word, but it basically allows you to form polymer structures at the nanometer scale or at the tens of nanometer scale. You can buy a machine that can do that, and it's used by researchers to make really exquisite structures with shapes that interact with light in unique ways, and shapes that can have really interesting mechanical properties, what people call these nanolattices. But it's not a scalable process beyond the lab. It might take 1 hour to make something that's 50 by 50 by 50 micrometers on a side. That's 0.05 millimeters on a side, right? Smaller than like a little segment you would snip off the end of one of the hairs on your head. So small, but enabling for research. I personally, from a basic research as well as technology perspective, I'm really fascinated about the possibility to combine the two. Combine additive manufacturing, 3D printing, where I might deposit some ingredients locally and then rely on the self-assembly to take over and put the material together. Yeah. In the end, I want to design any material. I want to say, can I make a solid that has a certain combination of strength and toughness, or electrical conductivity and thermal conductivity, and if I can understand the building blocks, just like I might take Legos off the shelf here in my office and put them together. I want to learn those instructions and build the tools to let me implement those instructions.
Yeah, no, that's an interesting point, and I like this. Also, this point about combining bottom up and top down, and I completely agree with you. And I think sometimes those terms lead people to be too devoted to one or the other. In the end, it's going to probably be some combination thereof, and that particularly at the nanoscale, it's really hard to bridge length scales. So there's certain things that are really good at certain length scales, like chemical reactions at the nanoscale, kind of bottom up, bringing atoms together. But if you try and keep going to build up macro scale objects, that can be hard from one individual block, right? So then you end up taking a bunch of nanoscale blocks and throwing those all together to build up the next set of length scales, and maybe those are printed in a top-down fashion. So yeah, I completely agree with that.
Yeah, so it's like the idea of hierarchy, building up. You can't necessarily, or you don't necessarily need to say, I want to control the position of all the trillions of nanoparticles, in the nano-manufactured, ultra-strong iPhone housing. But you might want to assemble nanoparticles into micro-scale blocks, and then micro-scale blocks into millimeter-scale blocks, and so on and so forth. And at some point, you may be able to pick them up and manually assemble them together using a process that we already have.
Right. Yeah, I'm reminded of the DARPA program, Atoms to Products, and that is kind of a central theme of that program. Is bridging these length scales with different processes.
Exactly.
Okay, so let's, with a few minutes remaining, let's talk about this fantastic TEDx talk that you gave a couple years ago.
Oh, thank you.
So I'm going to post it. I'll put it in the show notes so everyone can watch it and both get a sense for what carbon nanotubes are if you're not familiar, and who John is. And there's a couple things I want to ask you about. So the first thing is, I think a lot of people would agree with me and say that TED has been a fantastic influence on the public debate about a variety of things, but particularly science engineering. It's been really helpful to see people give engaging talks on topics that are important societally and haven't gotten as much play in recent years. So that I think is great. And I'm curious how you thought about preparing for this. I've never gotten a chance to talk to a TEDx presenter before, or a TED presenter. So when you were preparing, what were you thinking about?
So I was thinking about what was my message. I gathered that the TED conferences and TEDx conferences were all about sort of telling a story and having this 10 to 20 minute presentation send a a specific message. And the organizers of the TEDx, which was TEDx at the University of Michigan, where I was teaching at the time, had contacted me because they knew of my interest in communication of nanotechnology, and in particular, I had made what I called NanoBama, which was maybe like it sounds. It was a representation of President Obama in nano, specifically in carbon nanotubes. And what I told in the talk was the story of NanoBama, and moreover, what it taught me and told me about the process of and the value of trying to reach a broad audience with the underpinnings of your research. And if you want, I can tell quickly the story of NanoBama or leave it to the TED Talk. But it was very powerful to me, and I think probably valuable to many people to hear what a nanotube is and be engaged in learning a little bit about the technology, even though they were introduced to it by a picture of President Obama in carbon nanotubes.
Right, and I think you had this list, and people can go watch the video. You have this great list of the responses you got from people once this made it to the popular press. And my favorite one was the people that said, "What a waste of money. I hope this guy never gets another federal grant again." And, that goes back to what we started the podcast talking about, and that is you probably, through that work, made, let's say, 10,000 more people aware of carbon nanotubes, nanotechnology, in a way that the actual research didn't or couldn't. And so that ability to reach people is something that is so essential, and I think you said it best when you said we are compelled as scientists and teachers to do this kind of thing.
I think that if I'm fortunate to be able to do what I do for 30, 40, 50 more years, I may look back on NanoBama still as the one thing that reaches more eyes than anything I ever do, because it was printed on the front page of like the newspaper that you get given to you as you get on the subway in the morning, not only in Boston and cities around the U.S., but I heard Tokyo, Moscow, here, there, everywhere, featured by science journals, featured by blogs, on CNN, on BBC, everywhere. And the number of impressions it got was a result of the fact that it was, Obama was the big story. It was a historic moment for the U.S., of course. Any new president and Obama and being the first African-American president, as well as the fact that I think, the name was catchy and nano was catchy, and Obama had spent some time talking about science and technology, and it hit. I did not engineer it to be so popular, nor imagine it would be so popular. I did not engineer it as a political message, but it just happened. And let me reflect as I describe in the talk on how these things can be impactful.
Yeah, and I'm curious, as kind of a final thing here. You value science communication. You're clearly good at it. And I'm just kind of curious, is it something that you find comes naturally to you? Is it something you've had to develop and read about and actively try and improve upon? How's that worked out?
I mean, I think all of the above. I can't say it comes naturally to me, but I certainly found a personal interest in taking the initiative to do, what I call nanobliss roughly 10 years ago when I started putting up online pictures of carbon nanotubes that I was producing. I was interested in just what to me were beautiful pictures that frankly related from failed experiments. But I liked the visual appearance of them. And then, doing things like, NanoBama, which I did with my students because, I thought was fun and interesting and, nothing more. I said, I'm going to tell you I want to make Obama nanotubes. You're going to probably think I'm crazy. But then they were like, yeah, sounds great. Let's do it. And, we didn't spend a lot of money on it. We actually, the fine details, we put it on the edge of a silicon wafer pattern that we were making anyway for our research. So it didn't, quote, cost us anything more other than our time.
Perfect.
I built the website myself late on a Friday night, and then it happened. But yeah, this question of doing it intentionally versus serendipitously, I think, is a great one. And I say that it just has to be a matter of practice and initiative. I'll still always be doing my research and trying to let things relate from the things I natively do. But I think having an understanding of how to communicate clearly, connect to different audiences, from the most scientific and rigorous to the broader and more diverse, is important. And maybe to close, in one of my other talks about NanoBama, I was asked a very compelling question, like, how do you clearly you intended to do NanoBama, but how do you design things to have outcomes like that? I didn't say that very well, but you probably can see what I mean. Is it something you can do intentionally? And I said, I don't really know how to do it intentionally. You just sort of have to get in the game and practice it. And I'm really encouraged and inspired when I see students, especially new graduate students in my group, who say they want to learn to become better communicators and get involved in outreach and create better figures for their papers and create videos and those kinds of things. And as now the world gets bigger, we have more avenues for publishing, more people are publishing. Part of validating what we do, explaining the importance is about communication.
Completely agree. And with that, thank you, John, for taking a few minutes. This has been a really fantastic conversation.
Thank you. It was a great pleasure.
Thanks again to the Chi Foundation for their financial support. I can be found on Twitter at Michael Filler. I can also be reached via email at nanovationpodcast@gmail.com. I'm Mike Filler. See you next time.